Excellent. All right, we're going to start right now.
Sound quality good and all that
Yeah, sound
stuff?
sound quality looks great. Your video looks great.
Okay.
You're a seasoned professional.
I'm
Um,
wearing my infrared jacket. This has the emblem on it from Next Generation Space Telescope. So it's 2002 or before.
Man, it's funny. I did a history piece on JWST and sort of went all the way back to the beginning when it was originally the Next Generation Space Telescope, and people were shocked to hear that it might go to like $1 billion in budget and launch sometime in
Yeah.
early
Yeah.
in the early 2000s, and how little
Yeah.
did everybody realize what would happen.
Yeah.
Yeah, quite the history. But we'll get into that. We'll get into that. All right. So the question I always ask people is who are you and what do you do?
Okay. I'm John Mather. I'm the senior project scientist for the James Webb Space Telescope, and I work at NASA Goddard Space Flight Center just outside Washington, D.C., where I have been since 1976.
Wow. And like we could do a show just going through in great detail your background. But like, can we give us some highlights, because you've literally had your hands in every single major space mission, every major astronomy mission that people are familiar with. So just give us just a few of the missions that you've been involved in.
Yeah. Well, stepping back to before I was at NASA, I was at UC Berkeley to get a thesis on physics. I wanted to be like Richard Feynman and understand quantum mechanics and gravity. So people still want to do that, but I gave up on that. And I found a thesis project to measure the Big Bang. People had just discovered the cosmic microwave background radiation in 1965, and that was about 1970 that I was looking for a thesis. So my friends and I built a payload to send up on a high altitude balloon to measure the cosmic background radiation spectrum to see if it really is the black body curve that's predicted by every theory of the early universe that even resembles a Big Bang story. So
And what did you
it went
find?
up and it did not work. It did not work. So I had to write a thesis about a failed idea, and I got a job at NASA to become a radio astronomer. People thought I was going to be okay at that. It turned out to also be really hard. And after I'd been there for about 6 months in New York City at the Goddard Institute for Space Studies, NASA issued a call for proposals, announcement of opportunity. Anybody got an idea? And this is only 5 years after the moon landing. So I said, boss, my thesis project failed. We should try it in outer space.
Right. Not a balloon,
He
but in
said,
outer
right.
space.
He said, right, we should. He knew how important it really could be if it could be made to work. So we called up our friends. We wrote a thin proposal and we sent it in. And I thought, well, that'll never happen. But NASA knew that it was possibly important. And so 2 years later, I moved here to Washington, D.C. area to the Goddard Space Flight Center and started working to make that project happen. So it was conceived in 1974 and it was launched in 1989 and it worked.
And this was
And it did
COBE,
make
right?
it. Yes, this is COBE, the Cosmic Background Explorer satellite. It did work. It measured the cosmic spectrum and eventually down to 50 parts per million, which is about as accurate as you could have imagined in those days. These days, I could say my colleagues are working on a way to improve that another factor of 1,000,
Right.
at which point you get to see even more weird and wonderful things of the early universe. The
And
other
that
thing that the
map,
project,
like, that map that we're all really familiar with, that incredible view of the
yeah,
cosmic microwave
mhm,
background, that first picture came from this satellite, that full all sky survey of the cosmic microwave background.
yes, it really did. It was the first one that could see the whole sky. We were barely able to see the cosmic bumps, but there they were. And we felt very fortunate because we had no idea how hard we would have to try. The instrument was just barely good enough to do this, but it was so important that two other satellite missions have been flown since then, the Wilson Microwave Anisotropy Probe and then the European Planck mission. And they both said, you got the right answer the first time, but we have more detail for you.
Yeah.
And so it is now extraordinary what can be learned from this. We have measurements of the parameters of the expanding universe down to a percent level, which is completely unexpected to me when we instrumenters started dreaming about what we needed to do to measure something that had never been seen. And now the incredible statistical power of all sky maps has really come out. Basically, nobody expected this when we started.
Yeah. So give people some context. Like when you look at one of these pictures, and I'm having to use everyone's imagination right now, but I'm sure you've all seen it. It looks like this sort of egg on its side of different colors, blues and greens and yellows and reds, that makes up this background radiation of the universe. What are we seeing?
Oh my goodness, we are seeing the universe as it was when it was about 400,000 years old. We look out in all directions and we see radiation that came from those times. And why is it that? Well, it's because that's the time of the expanding universe when it became transparent. The early universe was hot plasma, and light waves could only go a tiny distance before they hit an electron. After it became a neutral gas, then the light waves were free to travel in a more or less straight line all the way from there to here. So we're seeing it as it was at that time. And now we can interpret the little hot and cold spots too. We don't know what originally caused them, but we know that most of them are there because of cosmic dark matter, which is something astronomers can measure but can't see. Mm-hmm. And that's important because those spots are also responsible for our existence. No spots, no people. So, and no dark matter, no people. So that's because gravity is the force that reaches across immense cosmic distances and can stop the expansion of the material in the dense parts. So the parts that are a little denser than average in that early expanding map could stop expanding. So that the map shows you how dense those little spots are and how and compares the large diameter ones with the small diameter ones. And so it tells us the initial conditions of the growth of everything that you see around you.
And before you launched the mission, were you expecting to see these differences in temperature, or were you expecting it to be all the same temperature?
Nobody honestly knew. When we first started, nobody had a decent prediction at all. By the time we launched, which was 15 years later, then people had worked pretty hard, and some people got the right answer. You should be able to get the right answer if you say, I know how the galaxies grow. They had to come from some seeds. Mm-hmm. And then you imagine back in time to see how this works. And so some people got it about right. But a lot of people were still surprised. And that was great for us because being a surprise means it's an important discovery.
We always joke about this on Astronomy Cast that the cosmic, like almost every big answer seems to keep coming from the cosmic microwave background. Like it just gives and it gives and it gives. Like, do you think there will be some limit to, like, will it always be useful to study the cosmic microwave background, or will we get to some point where we sort of learned everything we can from it?
Good question. Well, we haven't quite gotten there yet. There is one thing that's still left to learn that we know about, which is the polarization pattern.
Right.
So if you had sunglasses on and you rotated them in front of the sky, you'd see the sky would get lighter and darker because of the way that light scatters from molecules in the sky. We actually do the same thing with the early universe. We have put our sunglasses on and we rotate and we measure the polarization vectors of those hot and cold spots in the maps. And the remarkable thing is that there is a kind of pattern that could only come from gravity waves in the early universe. Before all that radiation became free to travel, uh, there was something going on. And so we'd like to know what it was. So this is a way of seeing what was happening even before the radiation was free to move. And so it's extremely important. It tells you something about physical properties of the material of the Big Bang, or I should say the early universe.
Right.
So,
Um,
how does this tell you? We know if a sound waves in a gas, there's only one kind of way that works, compression waves. And the compression waves, sort of going towards you and away from you, pressure waves. In a solid, you also have sideways waves. If you knock a board with your hand, then the side wave waves go propagating down through the board also. So there's three polarizations of sound waves in a solid. There's only one in a gas. So we're kind of asking the kind of question of the early universe. Well, what kind of stuff is it made of? And so this is incredibly important for the big challenges of quantum mechanics and gravity.
yeah.
So,
I mean, the cosmic
I don't
microwave
know.
background
So there
is so. Oh, go ahead. I was going to say that it's just so fascinating, but it's also this wall that is 400,000 years after the Big Bang, and a lot of the really interesting things that happened in the universe happened before that point. And so this is one way to be able to peer further back in time than you can just by looking at the cosmic microwave background. Am I understanding that right?
Yeah, that's right. There are things that cause patterns in those spots. Um, and if you can understand that, then you've measured something that you didn't know before.
Right. All right. So, and of course, like for people who don't know, you were awarded the Nobel Prize for in physics for this discovery back in 2006. So, congratulations. So, you also worked with Hubble, which everyone's quite familiar with. But I would like to just sort of jump ahead to James Webb, because I feel like the story of the early universe, as we go from the cosmic microwave background to the early structure of the universe, this is the story that James Webb is going to be telling. So, like, what came next after that light could finally be released out into the universe?
My goodness. Well, after the COBE results came out, I was thinking, well, that was exciting. How can NASA ever do anything to top that? And the Hubble telescope was already up and working a few months after the COBE satellite went up. So I'm thinking, wow, what do I do now? So I started saying, well, when we know we're going to build a thing that ended up called the Spitzer Space Telescope, and it's only a little guy. The telescope is 85 centimeters across. And my friend said, well, that's not good enough. There's an awful lot more to know about that. I said, well, how about we make a telescope that unfolds in outer space? How about one that's maybe 2 meters across,
Right.
about twice as big as the Spitzer? Okay, my friends laughed at me and said, that's much too hard. We'll never do that. So I was completely amazed when I got a phone call from NASA headquarters that said, we are starting a study of this new telescope that's been requested by a committee that was chaired by Alan Dressler. And they said they wanted a bigger telescope. How about 4 meters in size at least?
Yes,
And to
please.
do infrared astronomy. And so I got this phone call and I dropped everything. I was working with Chuck Bennett to make a proposal for the Wilkinson Microwave Anisotropy Probe cosmology mission. I said, "Wow, this is my thing to do. I want to do this new telescope." So I jumped in, and that's what I've been doing ever since.
And how did it go from 4 meters to 6.5 meters? What caused it to sort of turn into I guess the monster that we know today?
Oh, well, goodness, there were several steps. One is that I'd been thinking about a deployable telescope that could be bigger than the rocket. Other people had been thinking about it too. And then it turned out the head of NASA, Dan Golden, had been thinking about it when he worked for a classified company called TRW at that time, because they knew they needed bigger telescopes for the Defense Department. So, okay, so he knew that it was not impossible. He knew that it could be done, and he understood that astronomers needed bigger telescopes. So, okay, so the way started to open up magically that even though astronomers said they needed a 4 meter, it was pretty obvious that to really answer the scientific questions, they needed a bigger one. You say, well, what scientific question drives such a big telescope? And the answer was the cosmology. Uh, we knew a prize to be discovered was what's the first object that grew out of the Big Bang? What are they like? We had by that time the beautiful Hubble Deep Field. We had fixed the Hubble telescope. It was working. We had a picture that said, it's not like we said. The early universe happened much more quickly. Galaxies grew quickly. By the time we can see them with the Hubble telescope, they're already fully formed and begin to look old. So we had hoped with the Hubble telescope that it would be capable of seeing the very first things growing. Answer was nope, can't do that. Need a bigger telescope that does infrared light because the things we're looking for are so far away, they seem to be expanding away from us so fast that the light that comes originally at visible wavelengths, ultraviolet even, is redshifted out, and you can only pick it up with an infrared telescope. So the answer was, please build us an infrared telescope that's bigger than what we had before. And we said, okay, then we better make it unfold because we can't reach that scientific goal without a bigger one.
So you had thought up the idea, or had been sort of throwing around the idea of building a folding telescope, but you hadn't settled on the wavelengths that it was going to be observing. And it was this.
No, it was just a casual sketches out of a few graphs, and my buddies laughed at me. They said that's too hard. We're not doing that, so I stopped.
Yeah, and then, but then as the astronomers came together and said, here's this epoch of the universe that we want to analyze, that's where the actual full size of James Webb came from, using that folding idea.
Yeah, well, there's that. There's also the visionary nature of NASA headquarters at the time was receptive to something bigger and more powerful based on new technology. They could see quite well that if you're never going to get a bigger rocket, you were never going to get a bigger telescope. And so we don't build the rockets, so they're as big as they're going to get almost. So you astronomers, you want a bigger telescope, you better make one that folds up.
Right, right.
The headquarters could see that this is an investment in our future. So let's do it.
And so
were very
and I mean, this was the end of the 90s when you started down this journey, and
yeah.
that's sort of like the beginning of my career, was about the same time, and I've now been doing this for 22 years, and we've just seen the launch of James Webb. What was it like to go through the ups and downs of shepherding this telescope to space?
Yeah, well, I never worried that it wasn't going to happen. I only knew that it was going to take whatever time it took. The reason for that is we knew that the astronomy community really, really needed this. We knew there was never going to be another way to do this science because nothing on the ground could possibly see through the atmosphere. We knew a small telescope was never going to do the job. And so this was a unique, untouchable thing. Nobody can do the science without this equipment. So, okay, it's just going to take whatever time it takes. And so I didn't worry about that. I just said, this is going to be exciting. It's absolutely worth all its effort. However long it takes, it's going to be worth it. And then enough other people believed that too, that although we had troubles with our budget and our plan, people saved the project over and over again when we needed to say, well, I'm sorry, we didn't ask for enough money. This is just a too hard a project for that plan.
Yeah.
That happened several times. There was even a time when a congressman said, well, put zero for the budget in this. So people came together and said, no, we need to get this. And Senator Mikulski, by the way, was always a powerful advocate for all science, but NASA in particular, well, she was pretty annoyed because she'd been let down by NASA. So she said, you better get this right. So please make a committee that will tell us that we're doing the right science, that we're telling us that this is the unique thing or not. And please make sure the test program is right because that's really hard too. So we had two external committees that reviewed our work and said, yeah, actually, it's true. There is no other way to do this. And they made some suggestions to limit the cost. There's some things you don't really have to do after all.
Mm-hmm.
So we did what they said.
And so now, I mean, at the time that we're recording this, we're sort of in these in-between times. The telescope is at its final L2 Lagrange point. The mirrors are aligning nanometer by nanometer, and we're seeing these first combined images of a star. So it looks like at this point we can all breathe easy. Like every part of it is working fine. The mirrors are working great. And now it's just coming into focus. When those first images come, what will we see?
Well, actually, I can't really know what we're going to see. We will select some really pretty, beautiful things to demonstrate that the observatory is working. The list of those targets is secret, and I haven't even seen it. Because it will be a wonderful surprise for everyone. But all those beautiful pictures with the Hubble, they will be beautiful and different with the Webb. So obvious candidate objects will
right.
Places where there are an awful lot of stars together, like the other galaxies, like the Magellanic Clouds. Places where the stars are being born today, like the Orion Nebula, like the Eagle Nebula. And of course, we'll be looking at other stars and even our own little planets way in the outer solar system. So I'm not sure what they're going to be choosing as the very first things to prove this equipment works. But as soon as we get those few done and we start serious scientific observations, then we have a whole year of scientific things that are already being planned.
Well, let me revise my question then.
The long-term plan.
I mean, I guess.
Sorry. Go ahead.
I was going to say just like not necessarily like which objects specifically we're going to see, but I guess you have been dreaming, like you've been living in this place in the universe, right out at the very edge of what is possible to see. You're seeing this afterglow left over from the Big Bang itself. What do you hope to see? I mean, the James Webb will take this region of space that has been invisible to us to this point and lay it out finally in front of us so that we can take a look at it. What are you hoping to see?
I am hoping to get some big surprises, and so I'm kind of speculating about where they might be. So, number one obvious territory is the early universe. We have this marvelous model of the early universe called the Standard Model, and it matches the information quite well until just in the last few years we've started to get a discrepancy. We have two or more different ways to measure the Hubble constant, the rate of expansion, and they ought to agree, but they don't. And the disagreement is getting interesting. So either we're missing something, or the universe is complex, or we just have fooled ourselves in some way. So any one of those answers would be interesting for us, but there's a big mystery. It seems to me there's a possibility that the early universe had another kind of object that existed only for a short time, and they have all disappeared. So there are none of them left to find today. So I wouldn't be surprised if that turns up.
Are you talking about like the population 3 stars, like the first stars?
Or population 3 object of some sort. Maybe I just don't know. It just seems to me that's an area of space-time that has not been observed. And so something could be hiding there.
Yeah. Yeah, I mean, like these telescopes, observatories, they are question manufacturing machines, not answering machines. For every answer they give you, they open up 10 more questions. And it feels like the questions are the most fascinating part. What's that? Why's that? How'd that get there? What's that doing?
Yeah.
Um,
I look at things the same way. Our job is not to go and test a theory. Our job is to go find something that we didn't expect. And so that's because fundamentally astronomy is like biology. It's an observational science. It's full of complexity. Um, Things hardly ever go according to a simple theory. We're lucky when we can find a simple story to explain a complicated situation. But nature just goes for complexity all the time.
so we've talked a bit about the early universe. What are the limits? Like, is there still a hidden part in the early universe that even James Webb won't be able to reach?
Good question. We honestly can't tell what the early universe is hiding. So we designed equipment that is able to see the objects that we know about out to certain distances in space and time. And so I can tell you what those are. We think we should be able to see the first objects at a redshift of about 30. That is to say, when the universe was compressed by about a factor of 31. Things come that much closer together. So that's an enormous compression. That's a density compression of more than what is it, 30,000. So the universe was extremely different in those days. So something could have been odd, weird. So the big question astronomers have is what happened first? Did the galaxies grow in those dark matter blobs that we were talking about earlier? Or were there black holes out there that were there all along? Right now, we see that every big galaxy has a big black hole in the middle. But how did that happen? Did the galaxy make the black hole, or did the galaxy grow around the black hole? That's one of the big stories to test. We currently have an idea that galaxies grow by pulling 1,000 little bits together, that the little ones form first and then gravity pulls them in. Um, so here's a possibility. Each one of those little ones has a black hole in it. Now the gravity pulls them all together. The black holes find each other. So how does that happen? Well, we'd sure like to know that.
Yeah. I mean, again, it's funny because it's sort of like all of this time, these decades of work is all leading up to this next year. Starting in just a couple of months, we're going to start getting just report after report, which is going to be filling in all of these pieces, and it's hard to even imagine what astronomy is going to look like post first light. So we talked about the early universe. Let's talk about things that are a little closer to home, which is being able to observe the atmospheres of other planets. What will James Webb be able to do from that perspective?
Okay, well, we have two ways. If a planet is really bright and really far from its star, then we see it as a little dot, and we spread out its light into a spectrum, and we do chemistry on that because each different molecule or atom absorbs light at the particular wavelengths. So then we can see what's there if it's that kind. The other kind we can see is when a planet goes in front of its star and blocks some starlight. Then a little bit of the starlight goes through the atmosphere of the planet on its way to our telescope, and we can figure that out. How much of it went through that atmosphere and how much were the molecules in that atmosphere taking out of the starlight. So we can do both. This one is capable of observing tiny planets, Earth-sized planets going around tiny stars called M stars. And we got a lot of them in the catalog that we know about. We know when they're going to go in front of their star, and we know when we should observe, and we know how to set up the equipment. So we're going to try that and see what happens. So either those little guys are little rocks with no air, or they're little rocks with air, or even a lot of air, or at some point when they get big enough, you rather expect them to have a lot of gaseous material, and maybe there's no rock in the middle. So a lot of things to be found out. This will be the first time that we can observe atmospheres of small planets.
I think about like the TRAPPIST-1 system, because we've got this place where there's like 6 planets orbiting around this red dwarf star. Some are too close, some are too cold, and some are right perfectly in the habitable zone, and all pass in front of the star, and we'll be able to kind of see the differences with James Webb from the different planets as they're going around the star.
Yeah, that's a fascinating system. There are so many planets so close together, and it's pretty easy. It was easy enough to discover that this system was discovered from the ground. And that's possible because the planets, some of them are relatively big and the star is really small. So that was possible. And we still aren't able to do the atmospheric characterization from the ground, but we'll give it a try with the Webb telescope.
Yeah. Now we've talked about the early universe. We've talked about exoplanets. Where else do you see James Webb revealing information about the universe? Where else do you see it being used?
Well, obviously, one of the big mysteries we've had all along is, well, how do planetary systems get formed? So you may not be able to see the planets in them, but you can observe new stars growing in those beautiful clouds of glowing gas and dust, like the Orion Nebula, like the Eagle Nebula. Those beautiful pictures we make with Hubble show you the places where it's happening, but they also show you dust clouds. And why is that important? Well, number one, the dust is responsible for the formation of the stars. It enables the area or a particular place to get colder and colder and colder, so the gravity can pull the material together. But then it hides the results. There's a star in there and you can't see it because it's hidden inside the dust cloud. So this is where the infrared capability of the Webb comes to be so important. Infrared light can go around dust grains as compared to just bouncing off like the short wavelength.
Did I lose my internet?
Oh, I'm still here.
Okay, all right. Yeah, I'm on Starlink, and it's it's a little testy, but it allows me to live in the forest in Canada and be able to still do my job. So
wow.
Every now and then. All right. Well, so we've talked quite a bit about James Webb, but there's a lot of other projects that you have your hands in, and I'd love to talk about the future, because you had to draw a line with the capabilities of James Webb. I'm sure you were imagining, like, what if we have it fold out even more? Let's maybe make it 10 meter, 20 meter. Where do we go next? What kind of telescope do you think is needed to answer the next set of questions? Because you got to start now. I mean, obviously you can't wait for James Webb to generate all the questions. So what do you think should come next?
Okay, well, in a way, I don't have to figure that out myself, because the National Academy of Sciences just ran a committee and published a report. I like to call it a science party, which means we get hundreds of people together to talk to each other to come to an agreement about the answer to your question. So NASA studied 4 different very large observatories for space, and the committee said, well, we're not going to choose exactly an observatory, but we'll tell you what it needs to do. So we need something that's at least 6 meters in size, same sizes as the Webb, but accurate enough and covering the wavelengths that it takes to see Earth-like planets around other stars as little dots, little separate dots. So that way you can see the reflected light from the surface of a planet and learn a lot more about its chemistry. So that's like the hardest problem in astronomy right now, is to see those things. And of course, if you do this, it's like a super Hubble. It's about the same size as Webb, so it's a whole lot bigger than Hubble. But those are the shorter wavelengths, the ultraviolet astronomy that the Webb can't do. So that's the number one priority for that report. They also studied and reported on a far infrared observatory that would extend the Webb telescope results to much longer wavelengths and much cooler objects. And they also studied an X-ray telescope, which would be far superior to the ones that we have now, and tell you more about black holes and neutron stars and things that collapse and explode and things like that at extreme temperatures. So all three of those territories have been examined, and basically the committee said we need them all, but the first one to try is this optical and ultraviolet telescope that's like Hubble, only bigger and better.
Right. And I know, like, this is the LUVOIR telescope, and the original plan was something in the 9 to 15 meter territory, maybe bigger. But in the end, the decadal survey, I guess, brought the size down a little bit back to the Webb size. Do you think that part of that was just like lessons learned on taking on too much technical risk with James Webb?
Well, I don't know about too much technical risk, but it takes a lot of cost to solve all the technical problems. So in the end, it wasn't a technical risk for Webb, but it sure cost a lot of money to solve the problems. So
Yeah. Well, I mean, I guess like I know that, like, when NASA works on a proposal, they've got all of these things we know how to do. These things we don't know how to do yet. We're gonna have to figure them out as we build this telescope. And you only want to include so many of the we don't know how to do into your project. And that, I think with Webb, there were a lot of them in there. I mean, they had to, we can go on and on and on about all the new things that they had to figure out how to do.
Yeah, we had 10 inventions to make for the telescope to work.
Right.
So when we think about the upcoming future telescope, then I think it's pretty natural to say, well, that's about the maximum budget you all can possibly hope to get out of Congress. You better fit in there, or you're never going to fly at all. So that's what the committee thought could be done.
And with I mean, you mentioned one thing, being able to see, like being able to see the dot that is the light coming from an Earth-sized planet orbiting around a sun-like star would be just absolutely stunning. What else could we accomplish with a next generation telescope like that?
Oh my goodness. Well, you can see an awful lot more detail of everything that's here. We can watch the solar system do its thing. We can see galaxies much farther away. The early universe is a prime target for a telescope like that. Even if it doesn't do the infrared, that can see the very first objects. It can see what we call, I forget what my buddies actually call this, but there's a sort of time of peak activity when the galaxies were just growing as fast as they could. And that's at a modest redshift of about 3. Still, like, almost impossible to do with telescopes we have today. And it's you can only learn a little bit about those galaxies. But if you could get the bigger telescope, you could sure learn a lot more. So this story of how did the early universe produce us is it's got so many pieces, and the telescope is for that.
Now, you have you're active in so many projects at the same time, and the whole reason why I actually brought you on today was you were part of a team that was awarded a NIAC grant, the NASA Innovative Advanced Concepts Award, for explore a new kind of telescope called the Hybrid Observatory for Earth-like Exoplanets. So can you explain this project?
Sure. Well, let me start with a starshade. A starshade is something you use to cast a shadow of a star onto a telescope so that you can see the little planets hovering near it. And why would you do this? Well, the point of it is that the sun is 10 billion times brighter than the Earth. So if you're standing off at a great distance, you're trying to see a firefly next to a searchlight. So you can't do it without extraordinary optical quality or something. So this is one way. And so I worked on other versions of a starshade. I worked on a proposal to have one fly with the Webb telescope.
Huh.
That was too hard. We didn't do that. But in the back of my mind, I kept thinking, well, one of these days we're going to have a telescope on the ground that is totally immense, and there might be a way. So the answer is yes, there is a way. You can fly a starshade in space and cast a shadow on the telescope on the ground for long enough to measure something. And the upshot is with the biggest telescope that's being built today is a European one. It's called the Extremely Large Telescope, and extreme means extreme. It's 39 meters across. That's what, 6.5 times the size of the Webb telescope.
Right.
It means it's a whole lot bigger than this space telescope we've been talking about. So if you can do anything at all from the ground with this totally gigantic, immense telescope, then you better try. So that's my idea. Let's figure out how to do this. Now, why is it hard? The starshade has to be immense. It has to be about 100 meters across, which is about as big as 2 football fields side by side. And it can't be too heavy or you can't move it around. So this needs some very clever mechanical engineering.
So, and I actually did interview someone a few months back, actually talking about a fairly similar idea, but just sort of like using this starshade, you could cast a shadow, give I guess planet Earth little eclipses from these stars that fall right on the telescope, block that light, work with the coronagraph that's already built inside the telescope to be able to reveal the planets. How many shots at it do you think you would get if you had a starshade orbiting around the Earth?
Well, it's basically a matter of propulsion. Each individual object you want to look at needs a different orbit. And while you're observing, you have to push on the starshade to keep it exactly aligned. And so 2 wonderful propulsion problems to solve. And so when you run out of fuel, you're done.
Right.
Our designs say, well, it depends on how much fuel you can manage to get up there, but probably 100 targets could be done, maybe more.
And sorry, what orbit are you?
It's actually quite challenging.
What orbit are you proposing to put the starshade into?
Well, we're calling them astrostationary orbits. People think always geostationary, which means it hovers over your telescope all day long. We're looking for something that's different, that hovers between the telescope and the star for a while. And so it's not hard to find these orbits. They are pretty high altitude orbits, about 170,000 kilometer long ellipse will do the job. And at that point, the starshade is moving at about the same speed as the observatory is spinning around the Earth. So you match those up and you can do the job.
And so the propellant would be needed to then shift the starshade into a different orbit to set it up in a future orbit in front of a different object.
Yes.
Is that right? Yeah.
We need 2 kinds. We need propellant to hold the starshade in the line for the duration of the observation. And then we need another kind to go from target to target.
I see. So you would be essentially, it would be following this elliptical orbit, it would reach the top of its orbit, and then it would try to hover there for a while, giving the telescope time to take its data, and then it would stop propulsing, fall back down around the Earth, and then shift itself into a new location for the next target. And so would you be would you be essentially capturing, I mean, I'm thinking like 170,000 kilometers, so it's going around the Earth once every, what, 2 weeks or so?
Every 5 days.
Yeah, okay, okay, every 5 days. And so would you be observing a different target every 5 days?
No, actually, um, we'd probably do the same target 2 or 3 times before going on to the next one, because planets will move in
Right.
a few days, and we'll be able to see that. Um, so
Hmm.
actually, the propulsion that it takes to go from target to target is very slow. It's called solar electric propulsion, and so you can't move very fast, so you can't move very far. So it's going to take a while to do this.
So combining the largest telescope ever built by humanity, the extremely large telescope, which is like 39 meters, it's coming in 2026, with a 100-meter starshade, what can we get with that? Because I know that the ELT should be able to resolve Earth-sized worlds even without a starshade. So this has just got to be taking it to the next level.
Yeah. So um, the challenge is actually that the brightness problem. If the Earth-like planet were hovering out there all alone, it would be really easy to see it with ELT. It's got plenty of sensitivity. You could see them 10, 20 parsecs away in a short time. So now the job is just please block the starlight so you can see the planet. And so our simulations say in about 1 minute, you can get a nice picture of an entire solar system from Mercury on out to Jupiter with this target at, say, a distance of 5 parsecs.
Yeah.
And there are a lot of stars in that category. And then if you want to get a spectrum to say, well, what's in the planetary atmosphere, it takes you about an hour to do that. So that's not too bad. You could see oxygen and water in the atmosphere of a little Earth in an hour.
Huh. And so you would, like, on one orbit take a snapshot of the solar system, see if there's anything interesting there, and then maybe on the following orbits use more propulsion to have it loiter and let you do those longer exposures.
Yeah, that's probably what I would do. Um, Unless I get so clever that I can do it all at one shot, but that's
Right.
hard.
Right.
And I still want to see if the planets are still there the next time.
Right. Yeah. To see if they're in a different configuration. Um,
Yeah.
and
So by
so,
the way,
oh, go ahead. Yeah.
one obvious thing people always ask is, well, doesn't the Earth's own atmosphere block you from seeing those molecules in the other Earth out there? And you would think yes, but not quite, um, because the what we call atmospheric lines, the spectrum absorption lines of oxygen and water that we can look at the visible wavelength ranges are so weak that they are not completely blocked. And so, yes, we can definitely see oxygen and water despite the atmospheric interference of our own Earth.
And I guess, I mean, there's other wavelengths, like say ultraviolet, that you still would need a space telescope to be able to view, but there's going to be a lot that will be visible to the extremely large telescope, or the 30-meter telescope, or the Magellan,
Yeah,
all of these telescopes.
absolutely. Yeah.
Um, so I guess, like, what are the, I mean, you've received this NIAC grant to be able to study this. What are the big unknowns in your mind right now? What do you think are going to be the biggest challenges to
Oh,
make this work?
well, what I said in the proposal was I need to build something where the star shade has a mass of about 1,000 kilos. And that's about 1/7 of the mass that we extrapolated from a previous design that was done for smaller observatories, smaller telescopes for Jet Propulsion Lab. They studied star shades a good long time, and they're really good at it, and they made beautiful movies of them unfolding in space. And so you do know how to do that. But then when you try to get it to be 100 meters across, then it's too hard. It's too heavy. It takes too much effort to push it around. It costs too much. So my objective in this study is to think fresh and find a mechanical concept that is much lighter and is still capable of being sufficiently rigid and able to be put up there. So I think we can do it, but we're asking for a big jump in concept.
Right. Well, we are, like, at this point in early 2022, we are potentially just a couple of months away from the first launch of Starship to go to orbit. And that,
Mm-hmm.
if it works, and big asterisk there, if it works, then you will see a dramatic change in the whole launch equation. You're seeing
Mm-hmm.
well over 100 tons going into low Earth orbit. The launch costs on a reusable rocket coming down by orders of magnitude. Is there a part of your brain that sort of thinks about what could be possible with a rocket like that?
Oh, oh, absolutely. Not only can we put up bigger telescopes, we can put up bigger and better starshades, and we can refuel them. When access to space gets cheaper enough, then you say, well, it's worthwhile sending another rocket up with more gas. So that when I told you earlier that it takes a lot of fuel to push the starshade around, well, okay, just send more fuel. That's a possibility.
Yeah.
Also, it's pretty hard to fold up a 100-meter starshade to fit in any rocket, but if the rocket is bigger, it sure is a lot easier.
Yeah, I mean, like the fairing of Starship is like 9 meters. Like, you could fit James Webb without having to unfold inside a Starship launch.
Yep.
And a folding version would be 15 to 18 meters across if it just followed the same kind of functionality as Webb. And so
Yeah.
it's like, again, we're waiting for Webb's first light, and we're waiting for Starship to prove that this is possible. And if it does, then everything changes.
Yeah.
Um,
So, I don't have any doubt that it's going to work eventually. There's an enormous economic force pushing it. I think Elon is right that a reusable Starship is going to beat all the competition, and so he needs to build it. He's just going to keep at it till it works.
yeah, and even if it isn't fully reusable, I mean, still, that kind of a rocket could send your Starshade up, no
Yeah.
problem.
Yeah.
Yeah.
So I think it's pretty clear that if you could build a telescope that didn't need the starshade, it would be easier to use. But on the other hand, we already have this gigantic telescope coming, 39 meters across. It's extremely powerful. And so the things that it can do best.
How, and I guess, I mean, we're talking about before you've actually gone through the whole study process. You've essentially submitted the proposal and said, here's what I would like to investigate. Do you have any sense of, like, how long it might take to construct and launch, do you think?
Oh, I think quite a while. We're pretty far from having the concept that we would like. Right now, we're on the edge of impossible, and that's why it makes it into a NIAC proposal. If it were already something we knew how to do, it wouldn't be a NIAC proposal.
Right.
So if you win the NIAC and then you do a 9-month study, and then you propose for more, and then that takes you maybe a year and a half or two to do the next round. And if that works, then you get some more time and more money. So you're not even ready to start to the next stage for quite a few years. And that's presuming success, which
Yeah.
I would certainly anticipate, but you never know.
Yeah. Yeah. I love the NIAC awards. I mean, they've been running them now for quite a while, and a lot of the really exciting, interesting ideas that have ended up being more mainstream in NASA's mind started as these NIAC awards. It's sort of a great way to constantly be thinking about the future and trying out ideas. I think even the Starshade started out in that
Yes, it did.
as a NIAC
Webster
award.
Cash.
Yeah, Webster Cash. That's
Yeah.
right. Yeah. And then here we are. It's a very mainstream idea now, and there's a Starshade attached to almost every space telescope as a consideration. Anyway, well, John, if people want to keep track of what you're working on, what is the best place? Where's the best place to go?
Well, we haven't published very much about this one yet. Um, I didn't even expect to be chosen, but I'm pleased to be chosen. What I'm trying to do next is to create a way for public participation, though. People are very creative. And college kids in mechanical engineering have to build their balsa wood bridges. And I'd say, well, please tell me how to make a self-supporting starshade 100 meters across out of ultralight material.
Right.
So I think that would be a good challenge
Have you?
for every college engineering class.
NASA actually does a bunch of these challenges. They've got one right now about how to deal with poop on the moon, how to deal with power, how to reuse and recycle material on a moon mission, on a Mars mission. So this might make a great NASA
Yes, well,
challenge.
funny you should mention that. I submitted my idea yesterday
For
to that one,
one of those.
for one of the NASA challenges. Yes.
That's awesome. Yeah, that's great. I could just see like you just never run out of ideas.
Well, I'm counting on the world around us to have lots of ideas.
Yeah, yeah,
I am pushing the bound of, I think it's not impossible. And now, please show me how it is possible.
yeah. Well, John, it's been an absolute pleasure talking to you. I really appreciate it. Congratulations on James Webb launching, and as we stand now, mere months away from that incredible first light. And I
Well,
look forward to this and all of the new missions that you're working on.
well, thank you. Before we close, I just have to say this was not my project. This was 10,000 people working together to make this thing happen, this Webb telescope. And I am absolutely in awe of the talents of the engineers and the managers who managed to organize all 10,000 of us to do this thing together.
Yeah,
So those people are my heroes. Bill Oakes is our project manager, and I just love what he does.
fantastic. Well, John, thank you so much for taking the time to chat with us today. Uh, I can't wait to see your response when those first pictures come out. So I'll be watching.
Well, thank you, Fraser.
All right.
I'll be happy to talk more about all these things when they begin to grow.
When you finally have some new questions.
Okay,
All right. Take care.
excellent.
Thanks.
Thanks. Bye bye
Bye.
now.
Excellent. All right. Thank you so much.